Hey everybody. So I'm showing you a $100 bill for a very specific reason. I'm also going to show you a quarter for a very specific reason. We've been talking about the integrated rate laws, but we've been talking about it in kind of a way where we've been cheating a little bit. We've been having a very specific limitation in all of the versions of the integrated rate laws we've been looking at so far. Namely, we've only been talking about systems that have one reactant going on to form products. And so we really have only been worried about one thing changing in time. Well, because we only want to deal with one variable, monovariable calculus. But we know that real chemical systems don't behave like this all the time. There's not always just one reactant. Most of the time, there's multiple reactants, like in this reaction below. So the question becomes, how do we deal with systems where we have multiple reactants? How do we find the integrated rate law for a system that has two components that are changing in time? Well, one way to deal with it is to go ahead and do the multivariable calculus on the fact that I'm going to now have two things changing. Or the other thing to do is to go get a $100 bill. I'll show you what I mean by this in a couple of minutes. Or get a quarter. Right? A $100 bill and a quarter. Keep that in mind as we look at the next couple of slides. Okay, so here's what we're going to do. We're going to come up with a clever way to deal with multiple reactant systems. And I've got a multiple reactant system up here. In fact, we've seen this guy before. We, on the worksheet about a week ago, did the differential rate law for this reaction. And we found the result that I'm showing here. First in bromate, first in bromide, second in H+. And so we see here that we've got three things that could change in time, so I could go ahead and try to figure out the integrated rate law for x, y, and z squared. But you know what? I like calculus, but I don't like it that much. So I'm not going to do the multivariable calculus. What I'm going to do is I'm going to figure out appropriate reaction conditions so that I can turn this multivariable problem back into a monovariable problem. And it's going to require me to make the analogy to money. So picture that quarter that I showed you earlier. If I had a quarter and you said to me, hey, Dr. Crane, could I have a dime? Well, I could give you my quarter and you could give me 15 cents back. So I've lost a good percentage of that amount of money that I had in that quarter. But if I had that $100 bill and you said, Dr. Crane, can I have a dime? And I gave you $100, well, eventually, hopefully, you'd give me $999 or $99.90 back. It would be great if you gave me $999, but $99.90 back. So I'd still effectively have $100 for the first approximation purposes. That's what we're going to kind of do here in this system. We're going to make something, one of the reagents, essentially be our $100 bill, and we're going to make the other reagents be our quarter. This is what I mean. Let's take a closer look. So here's the same reaction. There's the rate law that we could have got from doing a differential rate law analysis with the method of initial rates and all of that stuff. But if I want to observe this reaction in time, if I want to follow this reaction in time and develop the integrated rate law for this reaction, I'm going to do something pretty clever. Instead of having x, y, and z squared, I'm going to take these three variables and I'm going to set up the system chemically to turn it back into a monovariable problem. And here's how I do that. And you can do this in any number of different ways, but this is the way I'm going to do it for this particular problem. I'm going to take my bromide initial concentration and my H+ initial concentration, and I'm going to make them much larger than the bromate's initial concentration. What is that effectively going to do? Well, as the reaction proceeds, it's going to make the bromide and the H+ behave as if they're constants, right? All three of these reagents' concentrations, as we have been looking at it in graphs, right, they're all going to go down in concentration. But if I can make the bromide and the H+, in a relative sense, much, much larger than the bromate, then as I lose moles of the bromide and the H+, they're still going to behave as effective constants. These guys, the bromide and the H+, are going to be my $100 bills. And so as I lose a couple of pennies worth, metaphorically speaking, of these components, they're essentially still going to remain unchanged. So what this allows me to do, now remember, I can do this because I, the experimentalist, am in charge of the initial concentrations of any reactant in my system. So what I'm going to do is I'm going to set the bromide and the H plus to be something like, say, 2.5 molar at the beginning. And my bromate, I'm going to set it to be equal to like 0.0025 molar at the beginning. So that we're talking about an order of magnitude difference between these initial concentrations. So then it's going to take this complicated multi-component rate law, and it's going to shrink it down into a system that's easier to manage. So instead of having 3 variables, it's going to reduce down to being a monovariable problem where only the bromate concentration is effectively changing, because now the bromate is the quarter in my monetary analogy I was just making. So as the bromate goes away, there's going to be a noticeable change in its concentration relative to its low concentration. So I can do this. The great thing is now that the bromate and the Br minus are now going to be constant, or excuse me, I'm sorry, I messed that up. Not the bromate and the Br, but in fact the Br minus and the H plus guys are going to be my constant. The bromate is still changing. So I can take these now effectively constant concentrations and tie them up with the original rate constant K to get a new rate constant I call K prime. And buried inside of K prime is that original rate constant, the bromide concentration, which is now going to behave like a constant, and the H plus that's going to behave like a constant. And as we see here, right, the reaction is still first order with respect to bromate. So if I were to go ahead and graph the natural log of the bromate concentration versus time, I'm going to get a straight line, the slope of which would give me K prime. And then I could determine that slope. I know my initial concentrations of bromide and my initial concentration of H plus, so I could actually work backwards and find out the true value of the true rate constant, K. So this really is nothing new. We don't have to learn any new calculus. We don't have to learn any new integrated rate laws. Everything will still be first or second or zeroth. All I've shown you is a clever experimental technique to take what's going to look like a multivariable problem at the beginning and reduce it down to a monovariable problem. The only thing you have to do is decide which reagent you're going to maximize concentration and which reagent you're going to minimize concentration. Now there's a few more subtleties to this, right? You see that one of my reagents is H plus. Now one way I could make H plus behave as if it were an effective constant is to, as I showed here, maximize its concentration, have lots of H plus in the system relative to the one reagent that's still going to change. But there's a more subtle way I could keep things like H plus or OH minus to be constant concentrations during the course of the reactions. I could set up a particular kind of a system for my chemistry. Does anybody know what kind of a chemical system we employ when we want to keep H plus or OH minus, these kinds of species that affect the pH of a reaction? How do I keep the pH of a reaction constant? What kind of a system do I use? I'm going to use a buffer. If I use a buffer, it keeps the pH constant. So it would have the net effect of keeping things like H plus constant. So I could swap the system with lots of some of the reagents, or if some of my reagents are things like H plus or OH minus, I could use a buffer system. Okay? So this is called pseudo-ordered reaction conditions, as you can see from the title here. Pseudo-ordered reaction conditions. The reaction really isn't, in this case I reduced it down to, it's really not first order, but I can get it to behave like it's first order, and then I can work backwards and find things like the true rate constant. Okay, we'll play around with the math of this in class a little bit later on. But I wanted to use the video to introduce this idea of pseudo-ordered reaction conditions. I'm not teaching you anything new other than having you think about experimental conditions you can leverage to make complicated systems look more simple. All right, we'll see you next time.